Hi everyone, my name is Neha Kartham and this is the lecture on printed circuit board fundamentals. In this lecture, we're going to learn about thermal management. Here, thermal management is the use of materials to transmit heat away from components to less critical areas such as heat sinks, metal core, or heavy copper plane layer. So why do you think this thermal management is important? It is important because when you have a circuit or when you have a circuit board or a device, let us take just the microprocessor for example. When you switch it on and you have all this circuitry working inside, we know that there will be heat generation because of losses I square R. So this heat is not removed or dissipated efficiently. Then what will happen? It is going to lead to a rise in temperature, and finally every device, because of its material constraints as well as the requirement of proper functioning, has a certain threshold temperature beyond which it cannot operate. Either its performance goes down, and in the worst case it just gets damaged, or if I may use loosely term, then we can say like the component or the device is fried. So as the heat is generated, it is important to remove the heat efficiently so that the temperature remains within that acceptable threshold. And that's why this thermal management is important. Now I'll move on to the next slide. Here this slide talks about the heat transfer, and the three key components of heat transfer are convection, conduction, and radiation. So this heat transfer is energy, is basically the energy in transit due to temperature difference. It is also thermal energy, we call it. So this heat flow or thermal energy flows from a higher temperature to a lower temperature, and for heat to flow a thermal gradient, which is basically a difference in temperature. A temperature gradient, we can say, it must exist in the process of heat transfer. So if you have like two bodies, and if you bring them together in contacts, and two bodies are at different temperatures, then one at a higher temperature and another body at a lower temperature, if you bring them in contact, then you know that heat will flow from a hotter body to the cooler body, right? And how long will that flow, or the heat will flow until the temperature gets equalized. So this is what we mean when we say that a temperature gradient has to exist when for the heat to flow. So here we can see that all these three important features of heat transfers are mentioned, and we are going to discuss them in detail later on in the next coming slides. Now this slide talks about conduction, and it says in conduction, heat transfer takes place due to a temperature difference in a body or between bodies in thermal contact without mixing of mass. The rate of heat transfer through conduction is governed by the Fourier's law of heat conduction. And here you can see this formula is given, which says Q is equals to negative Ka dt by dx, where Q stands for heat flow rate, and K stands for thermal conductivity of body material, and A stands for cross-sectional area, and dt by dx is the temperature gradient. And here in this picture it shows how energy is transferred directly by being in contact with this pan which is on a high flame. So this thermal conductivity is high, then if the thermal conductivity is high, then we can say that the material is a good conductor. So like copper is the good thermal conductor. Aluminum is also a good thermal conductor. But let's say brick is not a good thermal conductor, and rubber is not a good thermal conductor. Coal has a very low thermal conductivity, but it is an insulator. Now the conduction, this conduction also happens in a liquid or a gas, and the same expression holds good there as well. However, there may be other modes that may become predominant. All right. So this is conduction heat transfer. Now we'll move on to the next slide. Now this slide talks about convention. In convention, heat is transferred to a moving fluid at the surface over which it flows by combined molecular diffusion and bulk flow. Convection involves conduction and fluid flow. The rate of convection heat transfer is governed by this equation, which says Q is equal to HA Ts minus T infinite, where Ts is the surface temperature, T infinite is the outside temperature, H is the coefficient of convection. And here on the right hand side you can see that how the warm and cool molecules basically how they flow when the heat is given to the pan. So this convection is, you can see, is a transfer of heat from one place to another by movement of fluids. And this convection is usually the dominant form of heat transfer in liquids and gases. Here this heat transfer is not just happening because of vibration of molecules and transfer of internal energy from we know as we know from one layer of molecule to the next. But along with that, here we have the bulk movement of fluid molecules also that the heat is taken away from. Now moving on to the next slide. So this slide talks about the radiation. In radiation, heat is transferred in the form of radiant energy or wave motion from one body to another body. No medium for radiation to occur. The rate of heat radiation that can be emitted by a surface at a thermodynamics temperature is based on Stephen Boltzmann law, which is mentioned over here. Q is equals to theta T to the power 4, where T is the absolute temperature of surface, and this theta is basically the Stephen Boltzmann constant. So we understand that this radiation is basically the electromagnetic waves that is generated by any surface which is at a temperature above the absolute zero, and it is the only means of heat transfer between bodies that are separated by a vacuum, as in space environments. And now this convention which you have seen in the previous slide, convention and this radiation are the principal means by which heat is transferred to the ambient air. And in general, if you see, approximately 70% of the heat dissipation from electronic equipment might be through convention, and 30% by this radiation. Moving on to the next slide. Now here in this slide you see different heat sinks, and these are the design for heat dissipation of components which ensure that the maximum allowable temperature of the board material and the component is not exceeded under the operating conditions. So you can see these three different designs. This is thermal heat sink provided over here under this component, and this is copper foil heat sink provided under the component, and these are the spacers. There are different types of spacers which you can use in your printed circuit board. So these heat sinks or heat dissipation may be obtained by having basically having a gap between the board and the component using a clamp or thermal mounting plate or attaching a compatible thermally conductive material working in conjunction with thermal bus plane to the component. So we'll learn about these more in the next coming slides. Now here you see this heat sink device. So you see these are called your fins. You see these fins attached. So when you have a number of these fins attached one after the other, we get a heat sink. So on the left hand side you see a base and these fins. So this is the base and the fins attached to it in the form of a parallel plate. So this is forming like a parallel plate, and this type of arrangement is called parallel plate heat sink, and many people call it also call it as a longitudinal fin heat sink. And in this, air will flow through these passages between the adjacent fins. While passing through, it is going to extract the heat from each of these surfaces as well as the base. Now, instead of continuous longitudinal plate like this, we can also have fins in this form, and this is called pin fin heat sink. So in this pin fin heat sink, it has its own advantages. However, we are not going to get in detail of in those details, but it does increases the mixing of air. So you can see here that the airflow will not be smooth between the channels, and now the airflow will become more chaotic in this case, which is actually helpful in increasing the heat transfer coefficient. So this is a better design. Now moving on to the next slide. So this slide talks about thermal management considerations for both heat sinks. So I'll just quickly read all these considerations. First is method of heat sink mounting, example adhesive bond, rivet screws, etc. to printed board. We will learn about the adhesive bond later in the coming slides. Thickness of heat sink and printed board assembly to allow adequate component lead protrusion, automatic component insertion clearance, heat sink materials and material properties, heat sink finish, example anodize, chemical film, etc. And component mounting methods, example spacers, screws, bonding, etc. Heat transfer path and rate of heat transfer, producibility, which we already talked about this in the initial lectures, which means method of assembly, method of cleaning, etc. Dielectric material required between the heat sink and any circuitry that may be designed on the heat sink mounting surface of the printed board. Edge clearance to any exposed circuitry, that is component pads and circuit runs, tooling hole location and size, heat sink shape as it relates to the structure of heat sink printed board assembly. The heat sink should fully support the component. Do not allow the component the opportunity to tip during the assembly or soldering. So I think all these considerations were pretty straightforward, and I hope you understand what it says. Now moving on to the next slide, assembly of heat sinks to board. Under this we have first category as mechanical fasteners, and here on the right side an example of a mechanical fastener is given. Let's see what it says. The riveting is the preferred fastening method. So when you use this method, then the care must be taken in the rivet selection and rivet installation to obviate laminate damage. Screws should be used if the unit is expected to be disassembled. Closer contact may be necessary to resist vibration or improve heat transfer. So here the use of adhesives along with mechanical fasteners can actually alter the shape of the PCB, but it may help in a vibration environment. And here the dry film epoxy adhesives are preferred over liquids, as the bond line thickness and squeeze out is easy to control. Bonding temperatures should be as low as possible to minimize the shape alteration in the PCB. Now moving on to the next slide. So this slide talks about the broaching fastener, which is one of the example of the mechanical fastener. So it says broaching fastener is a knurled shank device that you press into a hole for a strong threaded or unthreaded attachment point in non-ductile material. So here one choice to eliminate a loose hardware problem is this broaching fastener, and these broaching fastener example is given on the right on this picture. These fasteners are installed permanently in all types of PC boards with the fewest number of parts, and they come in many types and each has a specific function and advantages. However, all types install simply, quickly, and permanently. So these it also says specially formed axle grooves around the shank of the fastener cut into a material for a firm fit that resists rotation. So here the broaching nuts make a permanent thread for board mounting when pressed into the PCB, and they come in steel or stainless steel, and mating screws completes the final component attachment when you use it for your PCB. Moving on to the next slide. Now here is another example of a mechanical fastener, and this is a right angle fastener and nut mount. So this is an example of a right angle fastener which you can use on the PCB, and this is another example. This is an example of a nut mount used on the PCB. So many standard types of surface mount fasteners basically are available, and spacers, if you see like spacers, they suit for board to board stacking. Nut mounts like this, these type of nut mount boards and attached components, and they are an alternative to broaching nuts and any loose hardware. And then we have another panel fasteners which we'll see later on, which suits to the application requiring easy removal and reinstallation of boards. And then we have these right angle fasteners as shown here, joint components at a 90-degree orientation. So this thing says the same thing what I've explained. Now moving on to the next slide. As I was talking about the panel fastener, so here is an example of that, of the panel fastener. So these panel fasteners basically come in several variation. They incorporate a threaded screw or a pin that retracts and advances to engage a nut or internally threaded piece of a hardware. So here you see the panel fastener, purple, plastic of ABS company, plastic caps and metal Phillips. Drive screws are supplied separately from the soldered retainer so that the retainer can be placed on the board and run through the oven. After the reflow, the cap and the thread snap onto the retainer to complete the installation. So that's how it is installed on the PCB. Now this is the another way by which we can assemble heat sink to the board, film type adhesive. And adhesives used in printed board assemblies are basically drawn from basic 5 types of resins, which are mentioned here: FRF4, multifunctional epoxy, high performance epoxy, bismillamide, cyanate. All these are the basic types of adhesive materials. And in addition to adhesion quality or bond strength, criteria for adhesive selection is also there, which includes like hardness, coefficient of thermal expansion, service temperature range, dielectric strength, etc. So it says adhesive films or sheets used for bonding heat sinks, stiffeners, etc. Or as insulators are generally in accordance with the IPC 4203 or IPC 4101. So these IPC standard it follows. And here in the picture you see film type adhesive material, and this type has many uses in laminated structure. Its ability to pre-cut a film adhesive to fit given size, given shapes or dimension is a distinct advantage in the fabrication of some laminated parts. So here and here you can see this adhesive film type is placed under the heat sink and on the top of the printed circuit board. So if we talk about the material of this adhesive, then let's take an example of the epoxy based film adhesives. They provide very good bond strength but require elevated temperature cure. Film adhesives are commonly are commonly used to bond board heatsink to the printed boards, and mostly in the SMTs. And in the through-hole technology, printed boards and heat sinks may be bonded together with a dry epoxy sheets adhesive to improve heat transfer or resist any vibration. Now here in this slide we will talk about the liquid adhesives, which is also an example, is also a way by which we can assemble the heat sink to the PCB. And as you know, with the continuing trend towards making the PCB small and making the components also small, presents the challenge of ensuring that despite their ever decreasing size, contacts and components continue to work reliably. Many solder joints on PCBs are therefore being replaced with more flexible electrical conductive adhesives. And to protect sensitive components, adhesives are applied to PCBs as a globe tops, as you can see here, coating or underfill for chips. You can see here the example of underfill. And these are all, you can see different types of adhesives provided on the PCB: conformal coating, electrical conductive adhesives here, globe top we have already seen, a damp plus fill, corner bonding, conductive die attached, SMD die attached, under filler, thermally conductive adhesive. This is the sheet one, film one, which we saw in the previous slide. Corner bonding, you can see this by this red color. Connector sealing here. So these liquid adhesive is a producibility concern, and because of the difficulty in application, associated cure cycle and alteration of the heat sink and printed board assembly, we need to consider the producibility. Now this slide talks about consideration for SMT board heat sinks. So heat sinks which are used in surface mount technology applications are either built within the printed board, typically copper layer laminated in the printed board, or are a solid plate that has a surface mount printed board bonded to one or both sides of the PCB. So now here in the design consideration, we have to keep in mind that vias under a heatsink should be avoided, and most adhesive systems use pressure during the cure cycle, which will allow the adhesive to flow away from the via, and this can generate a short between the via and the heatsink. And here you see an example of a silicon sheet adhesive which have been very effective in bonding printed boards to a solid heatsink. So the bonding, basically bonding integrity of this silicon sheet adhesives is dependent upon the proper application of a primer to the surface to be bonded. So care must be taken to prevent silicon contamination of surface which are to be soldered and or conformal coated. Now this slide talks about PCB thermal pads. I hope you remember in the Ki-CAD we made the we provided the thermal pads in our design, and for the PCB layout designer, a thermal pad usually means a large area of a metal that either a device solders to or a heat sink bolts onto. So these thermal pads they are also known as thermal relief pad, as you can see here, which are small voids. You can see these small voids in a metal plane around a through hole pin. In thermal pads, they are physical features that are designed into the PCB to help. They are designed such a way to help manage the heat either for cooling components or to assist in the soldering process of a through hole pin. So these pads, so here in this picture you see this is the component lead copper pad of the PCB without thermal relief, and this one is with the thermal relief, and here you can see these are the voids. So these pads are basically made from electrically insulating materials that conduct heat, such as a combination of a silicon and ceramics and and are tacky, allowing them to be easily applied to a PCB assembly. These thermal pads are usually positioned between a hot component and a heat sink to help conduct the heat from the component into the sink. Thermal pads, they can be much easier to work with when compared to the thermal paste, which is like a little bit messier. We're going to learn about that in the next slide. And here it says the same thing. Thermal pads is a special solder pad on the circuit board. This pad is connected to the surrounding copper core only within thin bridges due to thermal reasons. This prevents outflow of heat to the attached copper surface while soldering the component, and therefore negative effects to the soldering process. Now let's talk about the thermal paste. As you can see on the right side, this is the picture showing thermal paste on the printed circuit board. So by applying the thermal paste between the hot component and its heat sink, the paste will basically fill in any air gaps between the two. These gaps, if they are left unfilled, what will happen is that it would act as a thermal insulator, which in turn would basically hinder the heat from being conducted into the heat sink. By filling these gaps through, By filling these gap, the thermal paste maximizes the heat transfer, and it eventually dissipates through the heat sink. Now here, with the thermal paste, the big advantage is that its ability to easily spread. It will conform to uneven surfaces very well and fill large gaps more evenly than compared to the thermal pads. And this is what makes thermal paste more universal when working with unusual shapes or any different configurations of components. And there is one more advantage of thermal paste, and it is that with the ability to apply it as a thin layer, thermal paste can provide better thermal conductivity than the thicker pads. Now moving on to the next slide. So here I have compared thermal pads with the thermal paste, and these are some of the advantages and disadvantages of both of them. I'll just quickly read them. The advantages of thermal pads include they can be easily handled, it can be cut into specific shapes, no mess, easy application, no pump out, no dry out, range of materials with various specifications. Disadvantages: high manufacturing costs, intensive application. Whereas if we use the thermal paste, then it is more reliable, inexpensive, easy application, fills gaps well, thin layer. And the disadvantages are these: it is sometimes messy, it pumps out, dry out, requires pressure. So honestly, there isn't one clear winner over the other, as each has its own strengths and weaknesses. It all depends on the specific application you're using for. The important thing here is to carefully evaluate the thermal needs of your board and then choose which one will best serve to those needs. You may even find that you need to use a combination of two in order to give yourself the best thermal coverage. In addition to the thermal pads or thermal paste, you also need to design your PCB with proper through hole and surface mount pads. You need to route traces, power planes, and provide thermal relief pads, and this will go a long way in helping you to manage the thermal conditions of your circuit board. And to do this, you need to work with PCB layout tools like Ki-CAD, as you are already working with, and that will give the maximum flexibility in setting up these different design parameters. And you need precise control over your PCB pad shapes and LAN patterns, as well as design rules that will control the size of traces and thermal relief pads. So this is it. Thank you so much for watching.